take a breath. Now realize that 4 billion years ago, that same act would have killed you instantly. We are living in the aftermath of a planetary-scale poisoning that wiped out nearly every living thing on the surface of the Earth. If you want to know how our atmosphere became a cradle for humanity, you have to witness the moment it became a weapon. Our air feels like a permanent, invisible fixture, but it is actually a volatile crime scene. For the first 2 billion years of Earth's history, free oxygen did not accumulate in the atmosphere to fuel life. Then, in a geologically sudden pulse, the chemistry of the entire planet tipped. It was a transition that turned a CO2-rich void into an oxygen-choked death trap for the organisms that had called the planet home for eons. The mystery sits in the strata of the Earth itself, waiting to be unearthed. What singular event triggered this radical shift in our atmosphere? And how did the planet reset its own gas identity, fundamentally destroying a world to create our own? To solve the puzzle of our air, we must excavate the chemical memory of the deep past. We are tracking a transition that occurred over billions of years, moving from a suffocating, volcanic void to the oxygenated cradle we occupy today. This was not a slow, steady progression toward convenience. It was a violent, irreversible global catastrophe. Deep within the geological record, evidence reveals that a microscopic, alien-like life form unintentionally triggered a shift that fundamentally rewired the planet. This wasn't just a change in weather. It was a total environmental overhaul that reshaped the crust itself. We will see how this tiny organism effectively committed chemical warfare on the entire biosphere, a move that forced the Earth to forge 2,500 new minerals to stabilize its cooling exterior. We are investigating how our atmosphere, once a toxic graveyard for the life that dominated the planet, became a refined fuel source for everything that followed. The key lies in understanding how this invisible biological pollution turned into our greatest asset. 4.5 billion years ago, Earth was not the blue marble we recognize. It was a scorched, raw infant, spinning in the chaotic dark of a new solar system. Its original atmosphere was ephemeral, composed of little more than light, leaking hydrogen and helium. These gases were too thin and the planet too hot. They were stripped away, dragged off into the void by solar winds and the thermal energy of a world still colliding with debris. Earth stood naked, a volatile rock stripped of its gaseous shroud, waiting to define its own identity. It had no protection, no substance, and no air. It was a blank slate, hovering in the silence of space, completely unguarded against the radiation of the young sun. But deep within the planet, the pressure was mounting. A violent, internal engine was beginning to turn, preparing to vent a new reality into the vacuum. The first true atmosphere was about to be forged from the literal gut of the planet, but it would be nothing like the air we inhale today. The newborn planet was suffocating. As Earth cooled, the mantle buckled, forcing a violent secondary atmosphere upward. Volcanic chimneys erupted across the crust, churning out a suffocating shroud of vapor and gas. This was a world of carbon dioxide, accounting for nearly 97% of the air, laced with thick, suffocating nitrogen and sulfur. There was no free oxygen here, no molecule to fuel the metabolism that defines life today. Instead, the sky held only heat and toxicity. Water vapor, expelled in massive plumes, began to coalesce, turning the sky into an endless furnace. The planet stood defined by what it lacked, a chemical desert waiting for a catalyst to break the cycle. As we peer into the chemistry of this primordial blanket, we begin to decipher how such a hellscape could evolve into the cradle of biology. The answer lies buried in the very gases that choked the early world. Yet, the early Earth was not just a volatile furnace. It was a dry, desolate rock. If we look at the composition of that volcanic shroud, we find a missing variable: water. For the oceans to exist, they required an external delivery system, and the signatures hidden in our own seas point to a chaotic origin. Geochemical studies reveal that our water matches the isotopic makeup of carbonaceous chondrite asteroids. These weren't solitary arrivals. They were part of a relentless bombardment, a violent epoch of planetary assembly that pummeled the surface for millions of years. Every drop of the oceans that now cover 70% of our planet was carried across the vacuum of space, deposited in high-velocity impacts that shattered the crust. This was the true violent birth of our water, and as those impacts slowed, the vapor condensed into a boiling, iron-rich sea, priming the planet for something entirely new. Beneath those waves, the stage was set for a microscopic evolution that would eventually defy the very chemistry of the volcanic world. To find the pulse of this early Earth, we look to the scars of the Isua Greenstone Belt in Greenland. Buried deep within the rock are pilobasalts, formations that only take shape when lava erupts into liquid water and cools near instantly. These stones are 8 billion years old, dating back to a time when the planet was still a volatile, oxygen-starved furnace. Their presence is cold, geological proof that liquid water blanketed the surface just a few 100 million years after the Earth's birth. The existence of these seas, in an environment scorched by heat and heavy with volcanic gases, suggests that the ingredients for biology were already present. The chemistry was hostile, yet the water was there. And within those dark, primordial oceans, the physical conditions required for life had already been met. But the leap from liquid water to a biological engine was a hurdle that would test the limits of the primitive crust. The real catalyst for change wasn't just the water itself. It was about to arrive as a tiny, invisible architect. It was a quiet evolution, hidden in the shallow, sun-drenched waters of the early world, roughly 7 to 3. 5 billion years ago, a microscopic architect emerged. These were the cyanobacteria. They were not complex, yet they possessed a machinery that would permanently alter the planet's gaseous identity. By mastering oxygenic photosynthesis, these organisms cracked the code of solar energy. They took carbon dioxide and water, stripped them down, and used the energy to thrive. The byproduct of their success was a waste gas they didn't need: pure molecular oxygen. This was the end of the Earth's original, suffocating volcanic shroud of carbon dioxide and nitrogen. The era of the secondary atmosphere had reached its final act. But even as these biological engines churned, the oxygen never reached the air. It remained trapped, locked away in a chemical prison deep within the sea. Why was the ocean so hostile to this new element? And if the engine for change was already running, why did the sky refuse to turn blue for nearly 1 billion years? For nearly 1 billion years, the cyanobacteria worked. They processed light and carbon dioxide in the shallow, sunlit seas, pumping out a relentless stream of waste. That waste was oxygen. By every calculation, it should have transformed the world. Yet, as the gas bubbled up, it vanished before it could reach the surface. The early ocean was a vast chemical furnace saturated with dissolved iron stripped from the Earth's young crust. This iron was a glutton for oxygen. The moment the cyanobacteria exhaled, the metal seized the oxygen molecules, forging solid rust. These tiny iron oxides rained down in dense, heavy layers, cementing themselves into the seafloor. We see the archive of this era today in the banded iron formations, striated rock faces that look like the rhythmic pulse of a planet in a holding pattern. The ocean acted as a global buffer, a chemical sink that neutralized the oxygen and kept the atmosphere trapped in its volcanic, carbon-heavy identity. This was a world held in check by its own geology, where life was the architect of its own suppression. But the supply of iron was not infinite. As the mantle shifted, the chemical balance of the planet began to tilt toward a breaking point. The planet was on the verge of a transition that would tear the ancient, toxic order apart. The threshold had been crossed, and the atmosphere was about to be rewritten. For hundreds of millions of years, the rise of oxygen was a slow burn, a local trick of the tide. Then, too, 33 billion years ago, the mechanism snapped. In a geological heartbeat, a mere 1 to 10 million years, the oxygen levels in the atmosphere surged upward, breaking the shackles of the ocean's iron buffer. It was not a gradual incline. It was a violent, irreversible rupture. The Great Oxidation Event was caused by the exhaustion of the Earth's natural chemical iron sponge, forcing excess oxygen into the sky. The air itself shifted from a heavy cloak of carbon dioxide and nitrogen into a chemically volatile, reactive force. This was a planetary trauma. The very environment that had stabilized for eons dissolved, replaced by a corrosive gas that tore through the existing chemical balance. Across the globe, the oceans and the atmosphere entered a state of rapid-fire reaction. For the life that had dominated the Earth since its birth, this wasn't just a climate shift. It was the beginning of an annihilation. For billions of years, the world was theirs. Microbes thrived in a silent, oxygen-free darkness, their entire biology locked to an existence fueled by sulfur and methane. Then, the betrayal arrived, a slow creeping gas that burned them from the inside out. To these anaerobic organisms, oxygen was not the fuel of life. It was a potent, reactive poison. It ripped through their cellular structures, shredding the very molecules they relied on to survive. The Great Oxidation Event triggered an extinction on a planetary scale. It was the first true biological holocaust, a total purge of the established order. Lineages that had dominated the Earth since its molten infancy were systematically wiped out, forced into the deep, dark corners of the crust, where the atmosphere could not reach them. As the cyanobacteria flourished and filled the sky with their waste, they turned the planet into a graveyard for its original inhabitants. They were the biological engines of a new world, but they were also the architects of the most efficient purge in geological history. The old Earth died so that a new one could inhale, but the cost was an entire kingdom of life, erased in a breath. Oxygen did more than purge the archaic biosphere. It fractured the very crust of the planet. As this reactive, volatile gas seeped into the ground, it locked onto the exposed metals and rocks that had remained stable for billions of years. Surface iron rusted, turning the world into a red-tinted laboratory. This chemical assault triggered a mineral revolution. Before the Great Oxidation, the Earth's surface was remarkably simple, defined by a modest range of crustal structures. But with oxygen, nature began to experiment on a geological scale. Minerals reacted with the atmosphere to oxidize and hydrate, bonding into entirely new configurations. Over time, this biological fallout gave rise to over 500 distinct mineral species that had never existed before. The very ground we stand on is a product of this biological pollution, an inorganic record of the life that was sacrificed to produce it. The planet was no longer just cooling and shifting, it was rusting, and that decay would soon provide the final missing piece of the shield. As oxygen climbed, it met the relentless, burning edge of the sun. High above the clouds, solar ultraviolet radiations struck the rising oxygen molecules, shattering them. In that violent collision, oxygen reformed into ozone. This new thin layer of gas was invisible, but its impact was total. For billions of years, the sun's rays had struck the Earth's surface with enough energy to mutate or destroy any biological structure unfortunate enough to surface. The oceans had served as the only cradle, a liquid shield that filtered out the lethal light. The surface of the planet had remained a wasteland, exposed to enough solar radiation to mutate or destroy any biological structure. What then allowed life to step out of the water and colonize this once lethal frontier? With the ozone layer now anchored in the upper atmosphere, the rules of existence shifted, and for the first time, the planet was ready for life to step out of the water. The transition was a shift in power. For billions of years, life relied on anaerobic metabolism, an energy-starved existence that barely fueled the most basic biological processes. Oxygen flipped the script. When bound to organic fuel, it acted as a high-octane engine. Cells that mastered this efficient aerobic metabolism suddenly gained the surplus energy required for a radical leap complexity. This was the birth of the biological power plant. With oxygen-fueled energy as a reliable currency, life was no longer tethered to a microscopic scale. Genetic material became stable. Tissues began to differentiate. For the first time, single-celled organisms possessed the resources to coordinate, to adhere, and to build the first multicellular structures. These tiny clusters were the direct ancestors of every heartbeat, every movement, and every thought that defines the living world today. This gas did more than alter the atmosphere. It unlocked the biological blueprint for everything from the first complex organisms to the creatures that would eventually walk, crawl, and fly. But as life began to scale up, the environment it faced remained a volatile, hostile frontier. From the perspective of deep time, our atmosphere is a relic of a planetary crime scene. Earth began as a dead rock choked by a dense, thick veil of carbon dioxide and nitrogen. Today, that same sky is 21% oxygen, a volatile reactive gas that should not exist in such quantities if the planet were chemically stable. That surplus of oxygen is not a natural feature of Earth. It is the persistent, lingering exhaust of a biological revolution. The Great Oxidation Event was not a momentary shift. It was a permanent, planetary-scale poisoning. When those early cyanobacteria began dumping oxygen into the sea, they triggered a massive, irreversible chemical accident. They shattered the iron-rich equilibrium of the primordial ocean, flooded the atmosphere, and forced a mass extinction of the planet's original inhabitants. The rise of oxygen provided the energetic surplus required to fuel the metabolic complexity that eventually enabled human life. We are living in the quiet, oxygen-rich aftermath of that ancient pollution. Every breath we take relies on the waste product of an organism that fundamentally re-engineered the chemistry of the world. The mystery is closed. Earth's air is a biological artifact, a gas produced by life to sustain life, written into the very geology of our crust. We treat the air as a permanent fixed backdrop to our existence. Yet, look at the timeline. For nearly half of Earth's history, this atmosphere was not just different. It was lethal to everything we recognize as life. The oxygen we demand to survive exists today because a microscopic ancestor engaged in a violent, planetary-scale chemical hijacking. And as we learned, when that oxygen reached the upper atmosphere, sunlight converted it into the ozone shield that now protects us from lethal ultraviolet radiation, transforming a barren, irradiated desert into a habitable home. This current atmosphere is not a stable endpoint. It is a transient snapshot, a specific atmospheric ratio sustained only by the continuous, restless work of a global biological machine. The planet has changed its chemical identity multiple times in the past, shifting from volcanic poison to oxygenic abundance, and there is no rule of nature that dictates it must remain this way forever. Our home is not a finished product. It is an active, ongoing experiment in planetary survival. Look up. You aren't just seeing the weather. You are watching a process that is still underway. The planet is still breathing. We are simply here to witness the current phase of the cycle.